As a RF engineer, you may have heard and worked with a key figure of merit, which is noise figure or noise factor during receiver system design and analysis. Noise factor, by definition, deals only with noise powers. So consider this RF device. Let's say this RF device is fed with some noise from a noise source. Then you calculate two things. One is the total output noise power with all things considered, including the input noise source. And second is the output noise power only due to the input noise source. Now take a ratio. Obviously, the RF device has contributed to total noise and hence the noise factor is always greater than 1. Noise factor defines degradation of SNR by a device. So this is the other definition where it is the ratio of input SNR to output SNR. Let us look at this system with multiple blocks. Noise factor tells you the amount of degradation in SNR as the signal passes from one block to the next block in the system. Let's say the signal passes from this block to this block, from input to output. So as the signal passes from each block, the SNR is degraded. So why is it called degradation? Because as the signal and the accompanying noise pass through the system, each block adds its own noise, thus degrading the SNR, resulting in lower SNR at the output. Even amplifiers, which are supposed to amplify the signal, also add their own noise. Thus, SNR out is always lower than SNR in because now there is an additional component of noise added by the device or a block in the communication system. See this image here where an amplifier with gain G is given. Sin is the input signal and in an ideal noiseless condition Sout is G star Sin. But in real world environment input is always Sin plus Nin. Now, amplifier does not differentiate between signal and noise. Thus, at the output, what we get is Sout plus Nout. Thus, at the output, we get gain, which is multiplied both to the signal and the noise. But in the same real world scenario, the amplifier is also not a noiseless system. It adds noise, which is denoted by Namp. What we get at the output now, this equation plus N amp. Now let us go back to the noise factor equation, and now the noise factor can be written as ratio of total noise power at the output, which is N out plus N amp divided by the noise power at the output only due to the input source. Okay, so this is noise factor. So what is noise figure? So take dB or decibels of the noise factor, which is 10 log 10, and what we get is the noise figure, which is in decibels. There are two important points to note. First, it is important to note that noise temperature is assumed to be at room temperature. Scientifically, the number used is 290 Kelvin. If that temperature changes drastically, say like in space applications, then we need to use appropriate noise power values. Secondly, it is assumed here that all the gains are linear and each block is matched to the next one, typically which is 50 ohms. Without this, the gain is not the stated number and mismatch loss adds additional degradation to SNR. Thus, we need to keep these two important points in mind during noise figure calculation, which is temperature and the mismatch loss. In practical RF system design, non-linearity and mismatch is a real possibility and thus considered during receiver system analysis.
Please click on like and subscribe to our channel and click on the bell icon for regular updates.